All right, so why then do we need to talk about cycloalkanes separately? And the reason is that there's a stability difference. Because a number of things happen as we force atoms into rings like this. So what causes these things? So first of all, once we make a cyclic compound, there's no longer any free rotation. And you may want to put together some models of some of the smaller ring sizes, cyclopropane up through cyclohexane. Now, depending on what model kit you might have, you may find that some of them, especially cyclopropane, are quite tricky to put together. And we'll talk about what that means and why in a minute. But no free rotation. Now, if you recall, recently we discussed the idea of eclipsed versus staggered interactions. And in an acyclic molecule, it's not a big deal because our molecule has free rotation. And so if it's in a bad conformation, it can always rotate and get into something better. But that's not the case for a cyclic molecule. And so this no free rotation can sometimes cause forced eclipsing interactions. And then we'll also talk about bond angles, because that can cause issues as well. So let's start by looking at cyclopropane. At 3 carbons, of course, this is the smallest ring size we can form. But the bond angles here are just 60 degrees. They want to be 109.5. And so there's a significant distortion of those bond angles because of the shape. As a result, this causes very, very poor overlap of the orbitals when the bonds are forming. And results in much, much weaker bonds. The second issue, and this is one that you can't see very well in 2 dimensions, but it's one that you can see much better if you put together a model. And that's, if you put together a model, if you're able to, with some model kits you actually can't physically get the bonds to form. But if you're able to, and look down one of those carbon-carbon bonds, what you'll see is this. All of those hydrogens are eclipsing. And not only are they eclipsing, they're forced to eclipse, and there's no way for them to get away from that. And so cyclopropane molecules in general, cyclopropane rings, are not terribly stable. Now we can go up to the next ring, cyclobutane. Which initially we will draw like this. And as with cyclopropane, if this ring was planar, we would now have 8 CH bonds that are all eclipsing. Now, in order to avoid that, the molecule distorts slightly, and it's very, very difficult to represent in 2 dimensions. That's why I strongly encourage you to build a model. But if it distorts slightly into the third dimension, it causes two things. It relieves the molecule of the eclipsing interactions. And that's good, but there is a cost to that. If our cyclobutane was planar, our bond angles would be 90 degrees. But they end up being closer because it does this to being closer to 88. So again, we get some, we get sort of two issues. When this goes into three dimensions, we lose some stability because the bond angles get even worse, but we gain some stability because we lose the eclipsing interactions. But regardless, 3 and 4 carbon rings are in general not all that stable. And while 5, when we start moving up, 5 becomes a lot more stable. The most important ring size that we deal with is a 6 carbon ring, or cyclohexane. And that's because cyclohexane, as we're going to see, has essentially no ring strain. We're not really going to talk much about larger rings because it turns out our stability of rings, 3 is the least stable, 4 is a little better, 5 is actually quite a bit better, 6 is the most stable ring, and then as we get above that, 7, 8, 9, 10, they actually start to get less stable again. And that's because we end up with, again, hydrogens that are essentially forced to interact with each other. If your ring size eventually gets large enough, upwards of around 15 carbons, then the whole issue of ring strain just goes away. Because above 15 carbons, the rings are essentially large enough to act as if they're completely an acyclic molecule. But the final thing we'd say before we start getting into some of these more specific attributes of cyclohexane is, can you fit anything inside a ring? And the answer is generally no. Even though this is cyclic, unless your ring starts to get very large, and we're talking about probably more than 15 carbons, the ring isn't big enough for an atom to actually fit in the middle. But interestingly, there is actually a whole class of molecules known as catnains that were designed with just that idea in mind. And in fact, catnains are specifically we take a couple of large rings and we actually link them together. But for these, you typically need at least 18 carbons in each ring. But while a lot of these types of catnains don't really have much purpose, one of the more interesting ones, at least from a structural point of view, is this one. So while it's a little hard to tell from this drawing, this molecule was named Olympiadane, and the general idea here was that this was 5 interlocking rings designed to try and mimic the 5 rings you see on the Olympic flag. But the next video we're going to get specifically into cyclohexane. So before you open the next video up, make sure you've got your cyclohexane model put together and put all of your hydrogens in the into the model as well.